So far we know differentiation, and that tells us the slope of the curve, or the slope of the tangent line to the curve at a point. Now, today we're going to talk about integration. Now, before we talk about, anti-differentiation, same thing, but anti-differentiation. Before we talk about anti-differentiation, we have to know about differentials. So, if we have y, that's a bit too weird. If we have y equals some function in x, and we take the derivative of this function, we will get dy dx equals f prime of x. That is what the derivative would look like. Now, a differential is when you have dy and dx separated and they have meanings to each other. So if we can multiply dx by both sides, we get dy equals f prime of x dx. Now, if we take a look at this graph around, not like this, actually, it's not a good graph for the example. So let's do that. That looks nice. So, and if we were to estimate f prime at that point, x, it would be the slope of this tangent line right around here. So right around there. Now, if we were to estimate the slope, you would use the change in, that's wrong, change in y over change in x, or rise over run, if you learned that in Algebra 1. So, if you were to, say, hey, the change in x of this tangent line is right here, and the change in y of the tangent line is right here. But because it's a tangent line to the curve at that point, slope of the curve, we can call this dx and dy. Because the derivative is the slope of this tangent line right here at that point x. And if we find the slope of this line with the dy and a dy and a dx, the slope of the line would be dy over dx, which is the slope of the curve at that point. That's what the derivative is. So that's what the differentials are. And this would be the differential of x and the differential of y. So, well, let's talk about anti-differentiation. Let's say I were to give you f prime of x. Alright? Right? So, given f prime of x, would you be able to find f of x? Well, let's take a look at one example. Let's say f prime of x was 2x. Now we've done a derivative so often that we always see 2x here. And that would be the derivative of x squared. So, okay, we know f of x is x squared, and f prime of x is 2x. What steps did I need to take in order to get from here to there? This is also called the process of differentiation. So what did I do? Well, I basically took 2, put it down here, and subtracted 1 from the exponent. Now, what would you do to get from here to there, which is the process of antidifferentiation? Antidifferentiation. That's a long word. I'll give you a sec to think about this one. Okay. So, from getting f prime to f of x, well, I would have to, well, this is an exponent of 1, and I can just add an exponent, add 1 to the exponent to make this 2. How would I get rid of this 2 that came from here? I would have to divide by 2, or divide by my old exponent plus 1. Same thing. And I would cancel those 2, and we would get x squared. So, okay. But what if we had x squared plus 4? If we took a derivative of that, we would get 2x. Well, that's the same thing if we did from here to here. But there's a 4 here? How do we get it back? And if we had an x squared plus 5 or an x squared plus 7,028, these would all give me back a derivative of 2x. So I won't actually know what constant to add. So when I go the opposite way of any function whose derivative is 2x, it's basically x squared, right? All of these will have to have an x squared plus a number. So what we just write is we say, well, the antiderivative of 2x is x squared plus a constant c. We just write a c. Another name for antidifferentiation is integration. And we have a symbol for that, as like we have a symbol for differentiation. So, back to this diagram right here. This is called the differential form. And from here on, we use a symbol called an integral. And what we do is we just integrate both sides. We take an integral, we anti-differentiate each side. Now later on you'll know why we get y here, but to get the reverse of f prime of x, you integrate. If you want to find f of x, if you have f prime, you have to integrate. We have to find the antiderivative. So your original function y is going to be the antiderivative or the integral of f prime of x dx. This has to be here always. It comes from the differential form. It has to stay like this. And this is what we call a indefinite integral. Now, put this in a box here because it's important. Now, okay, we know how to get from here to here, right? Well, let's find out how we get the general case if we have some x to the nth power and we want to anti-differentiate. I'll put an integral sign here. What would be our f of x? And I'll put it f prime of x. So we do the process of integration to get back to our original function. So how would we generalize this to any x to the nth power? Okay, let's figure this out. If we have x to the nth power, and that's our derivative, or f prime of x, we go back to f of x by integrating. Now, for this general case, well, what do we do for here? Well, we took x to the nth, and we added 1 to the exponent, and notice that we divided by that old exponent plus 1. We divided by the new exponent plus 1, and notice how that's completely opposite. If we said x to the n, we'll differentiate that. We'll put xn minus 1 n. We subtracted 1 and then multiplied by n. Sorry, we put n in front first and then subtracted 1 from it. To anti-differentiate or to integrate, we add 1 first and then divide by the new exponent. So it's the complete reverse of differentiation. And that is an important theorem that'll come in soon about reversing and undoing differentiation. Okay. So I put a note here, so I think, okay, so here let me put, so we know 2 important things. We know the definite integral undoes a derivative. Put a dx there because that comes from the differential form. This is the indefinite integral. Okay. I want to make sure that's correct. Okay, so well, we know a power rule now, kind of. we know that if we take an integral of some x to the n power dx, that has to be kind of the reverse process of power rule when we differentiate. So this will be x to the n plus 1 over n plus 1. And there is an exception. N cannot be negative 1. And we'll find out why. If we let n equal negative 1, if we follow our rule, there'll be x to the 0 over 0. We cannot divide by 0, so there is an issue. No, we can integrate if n is equal to negative 1, but we cannot use the power rule. You will use this when dealing with transcendental functions. It will be very important. So this is like a simple power rule because there's a more general power rule up next. So these are the two important ideas that I will be discussing today. And I already did. So let's do some example problems, or let's just do properties of intervals first. So, okay. Let's go over some properties before we do anything else. Now, this is saying we're undoing the derivative and we get back y. Now, there's another equation that you'll see in textbooks, and you'll have capital F of x equals the definite integral of f of x dx. This is just the antiderivative. These are the exact same thing. I'm just using it for different notation and different purposes. I'm just saying that's the integral. That is a definite integral. That is a definite integral. It's just there's two different names. And sorry, that's indefinite. The heck did I just do? Indefinite. Anyways, this and this are saying the same thing, but this is putting down emphasis that to undo a derivative, you have to integrate, and you'll get back your function y. Here it's just saying the antiderivative is equal to the indefinite integral. That's all it's saying. Same thing, just written differently. Okay, so let's go over properties of integrals. Okay, properties of integrals. Before I go over properties, I want to make sure that if we have something like dr d theta equals f of theta, and I want to find and I want to find f of theta. I want to find the original function. I would have to multiply both sides by d theta and I'll get dr equals f prime of theta d theta, and then I can integrate. Wait, right here, that's a 1. If we use power rule, and there's an invisible r. Make sure that's the variable you're using, because the variable side, that was a lower, that was something that fell. But here is going to be the variable you're integrating. You should have variables with r in here. These variables must be matching. Must be matching variables. So this is going to be in r's. Well, if we add 1 to the exponent, this is r to the 0th power right now. If we add 1 to the exponent, we get r to the first, or just r. And that's why that equals r. Or that's why the dy turned into y. So, well, this is just the indefinite integral. So I'm just saying these variables have to match, and that's when you're finding your original function. So the properties are, if you have an integral and you have a function times a constant, this is equal to the constant times the integral of x dx. You have 2 functions of x, and you're integrating the sum of those 2 functions of x. Remember, you have to have matching variables. You're getting that could be the same thing as, hey, you're just separating those functions and integrating them individually. This works with pluses or minuses. If you're integrating 0 dx, this is a thing that equals a constant. Because, hey, if you take a derivative of any constant, you're going to get 0. That's why. Let's see. That's a property. Well, not really, but that's a rule. We gotta get over this. Okay, so those are most of the properties. There will be more showing up when we do definite integrals. Okay, so my video is going to be cutting up short real soon. So, okay, let's do some examples, then we'll do some trig integrals. Okay, so that's just a power rule, simple power rule question. That is equal to 3x over 3, remember add 1 to the exponent, divide by that new exponent, plus a constant because we can find. If we differentiate, we'll get back x squared no matter what number we put in here. Let's do another one. Okay. Right here we have a constant, we can pull it out, or we could just simply leave it here and act like we did in the differentiation. This is x to the 4th. And then we divide by 4, keep the constant. If we would have taken this away, it would just be 5 times x to the 4th over 4, which is the same thing as we just did right now. Plus some constant. Okay. If we have this right here, remember your life isn't over. You can simplify that to a rule. You can make it into the rule you know. So this is the integral of x to the 1/2 power dx. Okay, we can use power rule, simple power rule. Remember, add 1 to the exponent and divide by a new exponent. don't forget that constant. Okay. Let's go over some trig integrals. I'm going to quickly list off all the trig derivatives. I want you to pause the video and just test your memorization. So we have the derivative of sin x, the derivative of cosine x, the derivative of tangent x, the derivative of secant x, the derivative of secant x, and the derivative of cotangent x. So hopefully that's all of them. And then we're going to list the integral of kind of each thing. So, real quick, I'm going to just cut into pause when you are ready to memorize all of these. Or just name off the derivatives. I'll pause and give them out real quick. Okay, hopefully you got those right. Cosine, negative cosine, secant squared x, secant x, tangent x, negative cosecant cotangent, negative cosecant squared x. There's a pattern, a little bit of memorization, but there you go. Well, if the derivative of sine x is cosine x, and the integral of cosine x is sine x. I gave you a little bit of seconds to think about that one because you're undoing the derivative. You're getting back your original function. So, wait, the integral of sine x dx, wait, that's not negative sine x. We're just going to transfer that over to the cosine x. And there's a little proof here. If I put a negative out here and out here, wait, the integral of negative sine x is cosine x. This entire thing is cosine x. Oh, there's a negative there. Negative cosine x. I'm just making it easier for you. Just put in the sine x. The integral of secant x dx, secant squared x dx, is tangent x. The integral of secant x tangent x is going to be secant x. The integral of cosecant x cotangent x is going to be negative cosecant x. The integral of forgot the dx is because I was rushing so fast. That's a negative there. So sorry. The integral of cosecant squared x dx equals the negative cotangent x. Sorry for the bad handwriting. That is not a negative. Sorry about that. So this is negative, that's negative, and that's negative. And we gotta put our constants in here. Plus c. So that's your basic trig integrals. That's all the trig integrals that you have to memorize. And these are all the trig derivatives. So remember, you're just undoing the process. Integration undoes differentiation. And that's all your trig integrals. Remember your integral properties and remember your trig integrals and use those problems when you're integrating trig integrals or any simple polynomial. That's it.